Hello and welcome. Ever wonder why your phone battery dies? Chemical batteries have a secret. They're designed to degrade. But what if we could store energy using physics, not chemistry? We're talking about mechanical batteries like flywheels. They last longer, charge faster, and can handle hundreds of thousands of cycles. Today, we're diving into the insane engineering that lets these flywheels spin at tens of thousands of RPM without tearing themselves apart. Let's find out how advanced materials and clever physics are powering the future. Chemical batteries have a dirty little secret. They die. Slowly, yes, but inevitably. Every charge cycle degrades the chemistry a little bit more. Eventually, they need replacement. Mechanical batteries? Different story entirely. Flywheels can handle hundreds of thousands of charge-discharge cycles with sustained performance. Some large-scale systems like liquid air energy storage are designed for 30-year operational lifetimes with high performance throughout. Why the massive difference? It comes down to storage mechanism. Chemical batteries rely on material transformation, lithium ions moving back and forth through electrodes, which physically degrades the materials over time. Mechanical systems rely on physical displacement, elevation, compression. The primary wear mechanism shifts from chemical degradation to mechanical fatigue, which engineers can largely design out through proper material selection. Basically, physics ages better than chemistry. Who knew? Now, let's address the elephant in the room, or should I say, the massive force trying to rip your flywheel apart. When you spin something at tens of thousands of RPM, the centrifugal force is absolutely enormous. And here's the kicker: that force increases with the square of the angular velocity. So if you double the speed, you quadruple the stress. This creates massive tensile stress on the rotor materials. Engineers have to use sophisticated analytical modeling to predict these forces, accounting for things like variable angular velocity, viscoelastic stress relaxation, and acceleration effects. Every component has to operate well within its endurance limits because failure at 60,000 revolutions per minute would be, let's just say, spectacular. And it's not just constant stress. Every charge-discharge cycle introduces cyclic loading, which means fatigue stress. Over hundreds of thousands of cycles, you have to ensure that materials don't develop microscopic cracks that could propagate into catastrophic failure. The design process requires rigorous definition of rotor failure criteria and comprehensive structural integrity verification. This isn't optional, it's mandatory for both durability and safety. So how do engineers actually build rotors that can handle these insane forces? Advanced materials. Modern high-performance flywheels use hybrid composite rotors, typically layering different materials like carbon fiber and glass fiber, and there's some really clever engineering going on here. The entire success of advanced kinetic storage depends on material integrity. You can have perfect magnetic bearings and a perfect vacuum, but if your rotor material fails, none of that matters. The constraints are fracture, toughness, and strength under extreme centrifugal loading. Current research goals focus on developing sustainable, advanced technologies that deliver higher energy density, improved safety, and lower cost. Because right now, those composite materials aren't cheap. So let's wrap this up. The fundamental difference between a phone battery that dies in a few years and a mechanical battery designed for 3 decades is simple. Chemistry degrades, but physics endures. While chemical batteries face material degradation with every cycle, flywheels exploit physical principles rotation, elevation, and compression to achieve massive lifespan and endurance. The key to making them safe and durable lies in conquering the immense centrifugal force through advanced composite materials and rigorous structural integrity verification. The future of grid-scale energy storage depends on these breakthroughs, focusing on higher energy density and lower cost.